Hello everyone. In this session, we are going to think about transistor load line analysis. At the end of this session, students will be able to analyze a common emitter transistor amplifier using load line analysis. These are the contents of this session. Now, let us first think about biasing of what is the biasing of a transistor. So, the transistor is operated in desired operating region by connecting external DC voltage of correct polarity and amplitude to the two junctions of transistor. So, to operate transistor in desired operating region for particular application, the external DC voltage of correct magnitude and polarity should be connected to the two junctions of a transistor. So, this is called as biasing of a transistor. So, the biasing of transistor is nothing but actually we are establishing certain current and voltage conditions, certain DC voltage and current conditions levels for the transistor at the input side and the output side. So, these current conditions, current and voltage levels or conditions are known as a DC operating point, or quiescent point, Q point in short. Once the DC operating point for the transistor is selected in that amplifier circuit, it must remain stable. But practically, this DC operating point or quiescent point, Q point, that gives the value for DC collector current and collector to emitter voltage. That shifts, this DC operating point shifts or changes due to the variation in temperature sensitive electrical parameters of a transistor in case of practical amplifier circuit. But in any condition, this DC operating point must remain stable, constant. Now, this figure shows the circuit diagram for common emitter transistor amplifier. So, Vin is a input signal, low level, small amplitude input AC signal that is to be amplified is applied to the base of a transistor, and the output signal, amplified output signal is taken from a collector. R1 and R2 which are connected in series acting as a voltage divider biasing circuit used to forward bias the base emitter junction. So, voltage coming across R2 that is used to forward bias the base emitter junction, and VCC is used to reverse bias a collector base junction. So, single DC power supply can be connected using voltage divider biasing or self biasing circuit to operate a transistor in a common emitter circuit configuration as an amplifier. So, input current is base current IB, the input voltage, effective input voltage for transistor is base to emitter voltage VB, and output voltage of a transistor is a voltage at collector with respect to emitter, that is collector to emitter voltage. So, from that it is amplified output voltage is given to a load resistor RL, where RL stands for load resistor, and the resistance connected in collector terminal, that is RC, that is current limiting resistor, collector current limiting resistor RC, and the resistor connected in emitter terminal, that is RE, that limits the amount of emitter current I. So, this emitter resistor RE is bypassed using emitter bypass capacitor C. So, three capacitors are connected in this common emitter transistor amplifier. So, those are used to isolate AC signal and DC signal in the amplifier circuit. Now, what is the significance of load line analysis? From load line analysis, we can obtain DC load line and AC load line for a transistor working as an amplifier, as well as the DC operating point of a transistor. So, let us go for the DC analysis of amplifier. The DC analysis stands for the analysis of amplifier circuit considering only DC voltage and DC current. So, DC analysis is performed to obtain DC operating point, quiescent point, Q point, and obtain the DC load line for a transistor in a common emitter transistor amplifier. So, to perform DC analysis, we need a DC equivalent circuit. So there are two steps to convert a basic circuit of amplifier to its DC equivalent circuit. So replace all capacitors by open circuit. Replace all capacitors by open circuit, because capacitor behaves like open circuit for a DC signal and short circuit for a AC signal. So there are three capacitors. So I have to open those capacitors and ignore. The second step is ignore input AC voltage source. So reduce input AC voltage source to 0 volt. So using these steps, we can obtain the DC equivalent circuit for basic circuit of common emitter transistor amplifier. So this figure shows the DC equivalent circuit for a common emitter transistor amplifier. So the voltage appearing across a collector resistor RC, that is IC into RC. When a transistor conducts, current is flowing in the collector terminal, voltage will drop across RC. So similarly, the voltage will drop across emitter resistor RE. So using KVL, Kirchhoff's voltage law, we can write a voltage equation for collector emitter circuit. So write a voltage equation for collector emitter circuit. So starting from VCC minus ICRC, use a positive sign convention whenever we go from lower potential to higher potential. So we are starting from the negative point of VCC. So plus VCC minus ICRC minus collector to emitter voltage minus VC minus I into RE equal to 0. So as collector current IC is approximately equal to I, so we can assume IC equal to I. So considering the current flowing in the collector emitter circuit is equal to IC. So we can rewrite this equation VCC minus IC into bracket RC plus RE bracket completed minus VC equal to 0. So total load resistance for the transistor in the collector emitter circuit, output load resistance for a DC collector current, so that is RC plus RE. So let us designate RC plus RE equal to RDC, where RDC stands for DC load resistance of transistor in a DC analysis considering DC voltage and DC current. So let us rewrite the equation for a output collector current IC, DC collector current IC equal to minus 1 upon RDC bracket complete into VC plus VCC upon RDC. Let this is equation number 1. So let us compare that equation number 1 with the equation of general equation of straight line that is given by y equal to mx plus c, where m stands for a slope of line and c stands for intercept on y-axis. So equation number 1 represents the line of collector current IC, that is the output collector current IC, DC collector current IC. So from equation number 1, we can consider the extreme conditions for output collector to emitter voltage and output collector current. Let us consider minimum and maximum value for collector to emitter voltage and output collector current. When VC max is equal to VCC, substitute value of VC equal to VCC, then the value of IC equal to 0 from equation number 1. So from this we get a point A with x coordinate value VCC, that is the maximum value for output collector to emitter voltage, and y coordinate value is 0, that is the output collector current IC 0 on x axis. When we consider collector to emitter voltage minimum value, that is 0 from equation number 1, then the value of collector current IC, that is the maximum value of collector current IC, equal to VCC upon RDC, where RDC stands for RC plus RE. We get another point B with x coordinate value 0, that is collector to emitter voltage, and y coordinate value VCC upon RDC, that is the maximum value of collector current. So we can plot this point A and B on output characteristic of transistor in common emitter circuit configuration. So after plotting these 2 points, point A on x axis, horizontal axis, and point B on a y axis, vertical axis, we can draw a line between point A and B. A line drawn between point A and B is called as a DC load line, because this line is drawn under a DC operating condition. So considering only DC voltage and DC current. So why this line is called as a load line? Because the slope of this line depends upon DC load resistance of a transistor, that is RDC, given by RC plus RE. So slope of this line is negative. Minus sign indicates that the slope of this line is negative, that is given by minus 1 upon RDC. Similarly, we can draw a AC load line for a transistor. So before that, let us talk about quiescent point, Q point. So it is a DC operating point. It is a point on a DC load line. So that indicates that represents output collector current flowing in the collector emitter circuit, and the voltage appearing across collector emitter across a transistor. So this DC load line contains infinite number of such DC operating point or bias point or quiescent point, which gives the value of DC collector current and DC collector to emitter voltage. So DC load line contains infinite number of quiescent point or DC operating point. The circuit designer user can select any point on this DC load line as a DC operating point or a quiescent point, in short a Q point. The position of a Q point on a DC load line depends upon the application of a transistor. When transistor is operated as amplifier, the DC operating point is selected exactly at the center of a DC load line and in the middle part of active region of output characteristic of a transistor. Similarly, we can obtain AC load line for transistor. To obtain AC load line, we have to use AC equivalent circuit for the basic circuit of common emitter transistor amplifier. So for AC signal, there are two steps we have to use to convert that basic circuit diagram of common emitter amplifier to its AC equivalent circuit. To perform AC analysis, in which we are considering only AC voltage and AC current, there are two steps. Replace all capacitors by short circuit, because for AC signal, capacitor provides very low reactance. So this figure shows AC equivalent circuit for a common emitter transistor amplifier. So in that case, and reduce DC voltages to 0. Second step is reduce DC voltage to 0. So from this, the load resistance of transistor, considering AC analysis, it is changing from DC load resistance, that is RC plus RE, to RC parallel RL. So RC parallel RL, collector resistor comes in parallel with the load resistor RL. That is the load resistance for transistor, considering output collector current IC and AC collector to emitter voltage. So AC load resistance of transistor, that is RAC, equal to RC parallel RL, that is equal to RC RL upon RC plus RL. So another new line can be drawn through the same operating point, Q point, whose x coordinate is VCQ and y coordinate is ICQ. Value of collector to emitter voltage at Q point and value of collector current at Q point, with a new slope that is given by minus 1 upon RAC. So slope of this line, again it is negative, and slope of this AC load line is higher than the slope of DC load line, because RC plus RE is greater than RC parallel RL. So slope of AC load line is higher than a DC load line. Now student can pause video here and think over this question and try to answer this question. What should be the location of Q point on the load line for a common emitter transistor amplifier? The answer is, for a transistor common emitter amplifier, the Q point should be selected exactly at the center of a load line and in the middle part of active region of a transistor, so as to get equal variation, to get equal swing in the collector current IC and collector to emitter voltage for variation of input base voltage and base current above and below the Q point. This is the reference. Thank you.